said before, is a computer science professor at Virginia Tech and associate director for AI for social impact at Sanmay Center. He's received a PhD from MIT and his undergrad degree from Harvard University. His research focuses on one of the most challenging questions in contemporary AI, such as how algorithmic systems can be designed and governed to support the fair allocation of scarce societal resources. The title of his talk is on AI alignment in provisions of social services, opportunities and challenges. Addresses a question that is both technically complex and ethically central. Namely, what does it mean for AI system to be aligned with human values when it's used to support a decision about public services and social welfare? I believe this talk will be especially valuable because it invites us to consider AI as a socio-technical system embedded in a public institution with profound implications for equity, accountability, and trust. With that, it's my great pleasure to introduce Professor Sanmay Das. Please welcome Professor Das. I give you the microphone. Okay.
Well, thank you very much. Really an honor to speak here and be with all of you. So I'm going to dive right in. I'm going to be talking generally about an area that a little more than 10 years ago, when I was walking to University in St. Louis, I had a conversation with and therefore started a collaboration with my close colleague and good friend Patrick Fowler, who's a professor of social work and public health at WashU. And we started thinking about specifically the question of how to think about the use of AI in the provision of services to those experiencing homelessness. Okay, so in the course of doing this, I'm basically going to tell you a little bit of a story about some of the things that we've thought about in the course of the last 10 years. But as was, I think, the point was made repeatedly in the opening session, right? AI has changed a lot. Actually, it's interesting. It was just coming to mind that this is actually the 70th anniversary this year of the naming of the field of artificial intelligence, the famous sort of Dartmouth conference where the name came up was exactly 70 years ago. And I realized at some point that I've been working in the field of AI for more than a quarter century now, and it's been there all along. It's just that it hasn't gotten the kind of public notice that it's been getting recently. In fact, the joke in our field used to be people used to ask, "What is AI?" And we used to say, "AI is just whatever hasn't actually been deployed yet." Right? And today it's the exact opposite. Because the moment anybody does anything, it's AI, regardless of whether there's actually any intelligence in that system or not. And so, so I want to tell you a little bit about this, but in order to do so, I'm going to start with a little bit of a story to show you just how embedded AI is in all kinds of social systems. And this is from honestly way before the advent of LLMs and sort of the big things that have been happening. So I saw a story about a little more than a year ago in the New York Times, which captured my interest. So this is sort of unfortunately somewhat US-centric, right? So I lived and worked in the US, and so, but I think you'll see that the themes are very common, and I'm sure the exact same thing is happening everywhere. There's a lot of discourse in Europe about the use of AI in all kinds of public benefit systems and so on and so forth as well. So I think the issues are universal at this point. But in the U.S., right, so there was this issue where in the state of Nevada, the school system basically contracted with, or the state government that was funding education contracted with the company. And something interesting happened, right? It asked the company to provide AI software that would identify students who were at risk. Why? So that these students could then get extra support, extra services, which the state has budgeted for. So it's all a good thing in some ways, right? You're trying to identify students who are at risk. You're trying to do something useful for them. But then all kinds of stuff happened, right? So if you look at some of this, it says the AI system calculated that the state's previous estimate of the number of children who would struggle in school was far too high. Okay? So I find this interesting. First of all, it's anthropomorphizing the AI. The AI system decided. Secondly, I mean, hold this thought in your head a little bit. We'll come around. There's no evidence that it actually did this. We'll see what the cause was in a second when we dive through at least the public literature on this a little bit. But it says, number of students outside of the average plummeted to less than 65,000 from over 270,000. Okay, so that's a pretty big deal. That's a lot of students changing. But anyhow, so then I looked into another older article on this to try to get more information from the New American Foundation, which makes a good point that it's neither transparent nor better targeted. Well, we know that it's not particularly transparent how this is being done, but we don't really know if it's better targeted or not, right? What does that even mean? And so then I went through and found an even older article in Education Week, which you would hope, being an actual sort of trade journal in this area, does a little bit better in trying to explain exactly what happened, right? So, but there's a few things over here that stand out as well. This article starts by saying, the algorithm makes its predictions based on an assessment of 150 million student years worth of data. Oh my goodness, 150 million years student worth of data can't be wrong, can it? But this is what Arvind Narayanan and Sayar Kapoor, I think, refer to as AI snake oil, right? It's a sales pitch. So there is something interesting. It says that it employs a machine learning algorithm to assess the likelihood that each student whose data enters the system will or will not graduate. Now, this is sort of the essence of what's going on over here, right? And this is the way in which both AI has been used for a long time. And secondly, it's the kind of thing that AI is pretty good at, right? The thing that we got really good at, and I would argue if you go back, this topic is not about this, but I would argue that a big part of the success of AI is that we realized that we can turn a lot of things that we thought require intelligence and reasoning into instead problems of prediction. And prediction is what machine learning systems have become really good at. Particular kinds of prediction, there are still other issues, but we are pretty good at that, right? So I would not be surprised to learn that an ML system is pretty good at figuring out whether a student will or will not graduate given the value of data on that student. But here's the other interesting fact. This is how it's getting used, right? It's getting used for a particular kind of measurement. And yet, that whole thing, the big headline initially was, right, it cut the number of at-risk students from 200 and something thousand to 60,000. You know why it did that? It did that because here we'll get to it. The infinite campus system considers students who fall below the 5th percentile of all the scores in a sample to be at high risk, and students between the 5th and 20th percentile to be medium risk. It has these flags set in the software, and nobody bothered to change that in the state of Nevada. It does not matter what sample you give the algorithm. It will rank people, and then it'll say the top 5 percentile of this are high risk. Even if you give it sort of, students who have all qualified for the most exclusive university in the country, it'll say the top 5% are high risk, or the bottom 5%. Right? This is what sort of blew my mind, right? Like they basically did not look at this setting in the software that basically says, hey, this is the percent that we care about. And they were like, oh, look, it's got the number of at-risk students. It doesn't matter whether you're using AI or not. It doesn't matter if the ranking is completely random, right? It's going to get used. So this is a classic example of sort of, one of the issues with integrating AI into these kinds of decision-making systems is that people need to understand what the system is doing in order to integrate it with their decision pipelines, right? And they fail to do so in this case. But why am I talking about this example so much? Because I think it illustrates a lot of the core issues over here on the ways in which AI is getting used. And honestly, like it's integrated into so many of these social decision-making systems that, that this is really one of the use cases where we're thinking a lot about existential risk, and will AI agents become sentient and talk to each other and create private languages? Well, AI has been used for several decades in making really important high-stakes decisions of who gets money, who gets resources, who's eligible for a loan, all of these kinds of things that impact millions of people's lives on a day-to-day basis. And I'm worried that, like, we've lost the thread of that. There was a while when I think we were taking some of that seriously, but I think a lot of the stuff has moved away from thinking about that. And so I'd like to get some attention back on that if I can. So how is AI being used? Well, I'd argue that, at least in my sort of categorization of this, there's a few major ways in which it gets used. And today I'll focus specifically on the idea that AI gets used a lot for problems of measurement, right, in these human and social systems. And so, are we doing the right kind of measurement? Are we measuring the right thing? What is it that we actually want to measure is sort of a big issue over here. It also gets used for optimization, right? That is to say, okay, here's a complex decision-making problem. How do I go about allocating, bundles of resources to different sets of individuals or households in order to achieve the best outcomes? It's also being used to think about preferences and incentives. So, a common example of this is trying to audit for, is there fraud in people's representations of themselves in order to get social benefits or something like that? Are they telling the truth? How do I design systems that tell the truth? But at the end of the day, I think it comes down a lot to thinking again about sort of, I feel like, one of the major failure points that we've ended up with is kind of taking these systems as magical and able to solve all kinds of problems, where intrinsically there's a human problem at the core of it, which is what is it that we're trying to achieve? And then think specifically about how AI can help in achieving what our social goal is. And those social goals are intrinsically politically determined, right? There's always going to be trade-offs between what are the things that we are trying to achieve as a society, and that is not something that you can come up with a technical solution. However, I think that thinking about the problem from the lens of AI, where can AI be useful, can really help us clarify our thinking about the problem and what the true objectives of the system ought to be. So I find this interesting. Like, there's a little bit of history, right? I'll be talking about the allocation of scarce resources, right? Because in all of these situations, that's the key issue. This is something that historically, if you think about economics as a discipline, it considers itself the science of the study of the allocation of scarce resources in human society. The oldest quote that I could find easily on JSTOR on this dates back to at least 1945, or maybe even earlier, right? So this is from a review of economic studies paper. Economics is the science of administration of scarce resources in human society. And actually, computer science has also thought about these issues of fairness in distributing resources for a while. I found a 1962 paper that's talking about how do you share time in a massive sort of computer system back then, something which has come back to the fore in the era of AI after it disappeared for a while as a major concern. But because of this, I think that the ways in which we think about AI-enabled allocation of scarce societal resources are driven by the histories of these two fields, which have a real sort of quantitative focus in thinking about how to optimize things. And therefore, we're often thinking about measures of welfare that are the ones that have pride of place in economics. And this includes things like utilitarian measures of welfare, or even Rawlsian, where you're doing sort of a max-min, or Nash social welfare, other kinds of ideas of that kind. At the same time, we've been building real social and political institutions for resource allocation for centuries, and they often prioritize quite differently. One interesting example of this that I found was sort of, the New York City Marathon. This is the Planet Money episode on NPR, which is actually like very interesting to listen to, but it talks about the history of how officials' slots for running in the New York City Marathon are allocated. And it talks about how there's actually 4 different ways to qualify to run as an official runner. And this includes, you can enter a lottery, right, which is just by chance. You can do what is the merit-based qualification. If you've run another marathon fast enough, you can qualify for the New York City Marathon. You can pay your way into it. Now, not officially, you don't go over there and say, here's my money, take it, right? You can either say, I'm going to raise so much money for charity, and there's a minimal amount, and you'll get a bit number to run. Or you can buy a tourism package that allows you, like, among other things that are involved, you get a bit number to run. And finally, they want to keep local people incentivized to participate. So if you run 9 local races and volunteer at least one, then you can get a local participant. Right? So what are we doing over here? It's interesting. We've chosen, like, a plethora of different ways in which people can qualify for this scarce resource, right? A bid number for the New York Marathon. And this leads me to talking about the idea in political philosophy that really sort of underlies a lot of these kinds of allocations, which is the theory of local justice, which says, okay, if we're talking about allocation of resources, that first of all, scarce, and secondly, ones where we've decided that we don't want unfettered market mechanisms making the decisions, right? Then how do we do that kind of allocation? So this happens in areas like organ transplantation, where we typically don't want sort of, a free market in the trade of organs. It happens in homelessness resources, which is going to be my major focus. It also happens in education systems, in public education, and thinking about how resource allocation happens. So the specific setting that I'm going to talk about for the next sort of 15 or 20 minutes, I'm just going to give you a few vignettes from the kind of work that we've been doing in this is on homeless resource allocation. Okay, so now I'm going to give you a little bit of a cartoon version of this, and just in fairness, right, I'll warn you all, I am a computer scientist, and therefore I do think quantitatively, and so I'm going to abstract everything into sort of the simplest model that we can do anything useful with. There's a lot of sort of simplifications over here, but it's intended to capture the essence of what happens in the system. So we're going to talk about a system where typically, either if someone is experiencing homelessness or if somebody knows somebody who's experiencing homelessness, they can contact a hotline. That hotline does sort of centralized intake into the system. And if somebody is deemed eligible and there's room available in the system, they're typically allocated one of 4 or 5 different types of resources, ranging from sort of less intensive to more intensive interventions. So the most intensive over here would be transitional housing, which involves both finding people a place to stay and appropriate medical, counseling, and other resources. There are less intensive ones as well. But we figure out, okay, we actually have significant administrative data that tells us which resources allocated, a lot of demographic and other characteristics of the households, and then we learn something about sort of their future outcomes. And the future outcome that we care about in this case is, after receiving services, did they remain stably housed for the next 2 years? And the way in which we measure that is just whether they came back into the system needing resources again within the next 2 years or not. So, so that's sort of the version of this problem that I want you to have in mind as we go forward. And so just to give you a sense of the data that we have, this is for St. Louis, Missouri in the US. We have about 14,000 data points over the course of 7 years or so of people who are entering into this system. And you'll see that, their rates of re-entry are pretty high, but you can see a few things over here, right? Those who get transitional housing seem to re-enter at lower rates. Also, homelessness prevention has a much lower rate of re-entry, but that's because it's a somewhat different kind of intervention. Okay, so the population that is eligible for homelessness prevention is different systematically than the population that are getting the other interventions. Prevention does not necessarily mean, the technical definition of homelessness isn't necessarily that you literally do not have shelter, right? It could be that you live in a very cold place and you didn't have the money to pay for heating in the winter. So that's not a shelter that's habitable for you anymore. And so in those cases, prevention can do things like saying, hey, here's some money to help you turn your heat back on. So those kinds of things can also happen in these cases. Right? So it's a very sort of complex ecosystem, even defining what these problems are. Let me go back to thinking about the theory of local justice and just talk about sort of things that have been done. So this is the caveat that I was giving you earlier. Suppose I can reduce individual welfare to a single dimension W, right? A scalar value. Obviously you can't, but bear with me over here. Suppose you could do that. Then you can choose to prioritize based on several different things. And 3 of the common ways in which different systems do allocation are the following. So first of all, you could allocate by most vulnerable first. And that I will conceptualize as having the lowest W value when you're coming into the system. So this happens in homelessness, for example, where prioritization is often done based on a vulnerability score that tries to assess how vulnerable you are. It's also done in other areas. Liver transplant is a good example, where essentially the sicker that you get, the higher that you rise on the transplant list up to a point, and those who are highest on the list get highest priority for the next compatible organ. You could also prioritize based on who's going to be best off after the intervention. This is somewhat more rare, but it's a common critique of higher education in the US, at least, that the elite institutions are selecting those who are already going to do well, regardless of whether, regardless of what the institution itself is adding. Right. So that's another one. And finally, there's the idea of sort of maximum marginal benefit, right? Who is going to sort of, do, whose state is going to change the most based on the allocation of the resource? And this is something that came up a lot during the early days of COVID, right? People were talking a lot about ventilator shortages at hospitals and who should get access to ventilators in those cases. And the general sort of idea over here is that what you want to do is you want to prioritize those for whom giving them the ventilator most increases their probability of survival, right? Which of course leads to issues, but like basically if somebody is going to survive regardless, then you don't give them a ventilator, and if you think that they're not going to make it, then you also don't give them the ventilator, sadly, right? So this is referred to sometimes as the problem of abandonment, and typically we don't want to design systems that have that feature, but in cases of extreme situations like early days of COVID or battlefield triage, this is often considered a reasonable thing to do. And one point that I want to make over here is that in all of this, right, so one of the things of the bioethics movement of the 1960s was to basically say that in each of these, we want to treat each individual as kind of a unitary being with everyone sort of being equally valuable, right? We don't want to consider things like what value does this person have to society, like famously the Seattle God Committee was doing, as they called it in the early days of access to dialysis in these kinds of situations. Okay, so you could ask what happens without AI in many of these systems, right? Because most of these systems have existed for a long time before computers or AI were even around. And I really like this term that is due to Johnson and Chang, or at least they popularized it in the CS literature recently. This idea of the bureaucratic counterfactual, right? Which is to say that if you were not to use AI or just pure human judgment, what would be happening? And what is actually very commonly done in these systems is that people tally up some kind of a score and then they prioritize by that score. So I'm just giving you an example in the homelessness space over here. We've got to quantify vulnerability by giving points based on different features. So for example, if the age is greater than 60 years or less than 18 years, then you get 1 point for that. If you receive services for HIV/AIDS or mental health, you get sort of more points for that, and the more points you have, the more vulnerable you're deemed to be in these cases. Okay, so that's sort of the other side, right? Because people often talk about, don't use AI for this. You have to think about the counterfactual, right? What happens if you do not use AI? It's not that you're going to get some kind of perfect magical decision. You're typically going to get a decision that is based on these kinds of bureaucratic scoring systems. And the whole point of the Johnson and Chang paper is that these bureaucratic scoring systems are themselves often riddled with bias. Right? So there's all kinds of issues if you audit those systems as well. So what did we start off doing? Well, so our first idea was exactly to think about this problem of efficacy, right? And through this problem of measurement. So suppose we have different households, and suppose we can use machine learning usefully to predict what is the probability that this household will successfully exit homelessness, that is, remain stably housed for the next 2 years, conditional on receiving a particular intervention? We actually, so these numbers, these P's, are those probabilities that we estimate, right? What can we do with those? And the first thing that we looked at was, okay, can we use those and sort of reallocate counterfactually by saying, hey, let's take all of these assignments that happened in the past and just see if we move people around between different interventions, can we achieve more efficiencies in the system? Okay. So what we found over there was that, and I'm not going to get into too much detail about this, I want to focus on some of the later stuff, that yes, we can potentially, right, improve outcomes to some extent, but we're improving outcomes by about 5% overall. So it's not like huge, but there's potentially some significance to that. But also there's distributional consequences, right? 35% of households do better in the allocations that we would have done using AI in those situations, and 21% do worse. So there's potentially distributional implications, and it's not entirely clear sort of, what those would be, but there may be some benefits to using these kinds of predictive systems going forward. So then we started to think about, okay, what are the implications? And so I'm going to tell you sort of, 3 quick stories in the next 10 minutes or so about the implications of this early work on conceptualizing AI in the use of homeless services. So the first question that we asked was about exactly these kinds of fairness issues, right? When you do these kinds of allocations, or when you do any allocations, actually, you use this AI measurement, right? This AI measurement of possible outcomes. What is the probability of re-entry? To assess whether groups are being treated fairly or not. And the whole idea of this was to kind of, to some extent, marry 2 different literatures. There's a literature that has emerged on fairness in machine learning that asks these questions of group differences in outcomes, right? Are minority candidates not being hired at the same rates as majority candidates, for example? And at the same time, there's also a long existing literature in the economics and social choice areas on fair division, which asks a slightly different question, which is to say, are resources divided equitably among individuals, given the preferences of the individuals, right? So this starts taking preferences into account. So I'm just going to give you a little example to show something that's in my view quite interesting over here. Let's define 2 different measures, right? Let's define a measure of improvement, which is how much better do you do than you would do in your worst allocation. And let's define a measure called regret, which is how much worse do you do than you would in the best allocation that you could receive. So here's a cartoon example. Suppose I have 2 units each of resource types 1 and 2, and 1 unit of resource type 3. And I have 3 groups, right, of individuals, group A, group B, and group C, who all have sort of group-based sort of preferences or outcomes. So let's say that these are the utilities that they receive from getting these different types of things. So sometimes I do a quiz, but this room is too large for that. So let me just say, there's something. So what we can see from this, right, is that immediately you can see that resource type 3 is very well aligned with group C, right? The group C individual does very well with resource type 3. That resource is useless to groups A and B. So we should give resource 3 to group C in this case, right? Now that leaves 2 resources each of type 1 and type 2, and both group A and group B prefer type 1 to type 2, but group B does even better than group A does with a type 1 resource. If you're going to be fair across the groups, I would argue that the only sensible thing that you could do is say, hey, I'm going to give 1 resource of type 1 to group A and 1 to group B, and then the others of the other type, right? Now, I don't know who will get what. You can do a lottery within them or something like that, but that's the only thing that you would really consider to be fair to both group A and group B in this situation, right? But now if we measure regret and improvement, the one point that I want to make over here is that group A then does better than group B in terms of regret. That is, how well do you do compared to the best that you could do, because their best is not as high. But they do worse in terms of improvement because group B is improving more. Okay? So, in some senses, you might look at this example and be like, this is a bit silly, right? We don't usually do these types of interpersonal comparisons of utility, right? Does having a croissant give you as much pleasure as it gives me? Is not something that we typically like to think about. But at the same time, I would argue that over here, it's actually meaningful because if you think about a setting like homelessness or any other case where the utilities are coming to the system or the agency, then actually they're the ones who have to make these decisions about whether something is fair or not. And if one type of household returns to homelessness 20% of the time and another one 30% of the time, that's a meaningful difference, right? And so we have to think about these kinds of trade-offs in this case. And we've actually shown, so we've, mathematically, that you cannot simultaneously achieve fairness of both these kinds, improvement fairness and regret fairness, right? So you have to, in some ways, decide whether you want to evaluate based on how much better are you doing than you would have done in the baseline case versus how much worse are you doing than you would do in the best case that we could possibly arrange for you given the resources that we have. But this is a theoretical existence result. We actually then took it to the data to try to understand based on our data and our probabilities, like, what can we actually say? And we can actually show very similar kinds of things over here. So just to give you sort of a sense of it, if you look at, just if you look at the left picture over here, it seems to say that if you look at improvement fairness, households without children are doing better in the allocations that we make. Whereas if you look at regret fairness, households with children are doing better. And then the same thing happens if you look at black males versus white males in our data. By improvement fairness, you would think that we're favoring the black males, but by regret fairness, you would think that we're favoring the white males in the actual allocations that happen in these cases. So the metric that you choose, the way you choose to measure sort of, the results of your allocation systems is going to greatly influence whether you think that system is being fair to different demographic groups or not. All right, so that's sort of vignette number one. Vignette number two, right? What if I took these AI predictions that I'm making of, how successful will different interventions be? How does that influence human behavior? So what we'd eventually like to do is we'd like to do this with actual experts or caseworkers, but we haven't been able to do that yet. What we did was we did a pilot study with lay people, right? So we did an Amazon Mechanical Turk study, and we were asking this question of who should be prioritized for receipt of a scarce resource? Would you prefer to prioritize the more vulnerable or somebody who would have a better outcome? And so we did this survey with 520 participants. I just want to show you sort of the basic difference between, there's a lot of nuance to exactly how we set this up, but just to give you a sense of the basic difference in the conditions. Some people would receive only sort of this kind of information about the two households, right? So you can see it's just basic information that says things like how many members are in the household, what is the gender of the head of the household, what is their monthly income, how often have they called the hotline looking for services in the past, like, how many children do they have, like all of these kinds of things. The others would receive that information plus the AI predictions of how likely is this household to need future services if they are given intervention type 1 or intervention type 2. And they're told which interventions of transitional housing is the more intensive intervention, is more expensive to give, obviously, also more constrained. Emergency shelter is the less intensive intervention, it's less constrained. So two main results I want to share with you over here. First of all, it turns out people are very consistent in their preferences, at least when doing this task. They tend to either be vulnerability oriented or outcome oriented. They don't mix among these when you give them different possibilities. So that's sort of finding number one. Finding number two is sort of what I found really interesting over here, which is that suppose you do not give people these AI predictions, right? What do? In that case, their vulnerability or outcome orientedness seems roughly the same, actually. The groups seem roughly the same in how vulnerability or outcome oriented they are. However, once they get to also see the AI predictions, this actually allows them to reveal their true types in some senses. So for those who are outcome oriented, when they also see the AI predictions, their outcome score goes way up. For those who are vulnerability oriented, when they see the AI predictions, their outcome score goes way down, which means that their vulnerability score has gone up. Right? So in these cases, what is happening, when you provide them this additional information, it's giving them the information that they need to figure out, okay, based on my priors of, which type I should be prioritizing, this is the right decision for me to make. And it's interesting to think about sort of what the consequences of this might be in actual decision making. Of course, the big caveat over here is that at the moment this is being done with people who don't have a lot of experience on these problems, who are not sort of actual domain experts. So the last vignette I want to show you is like, what can we actually tell at this time about real experts, the people who actually make the decisions? And so this is deeply related to the theory of street level bureaucracy, right? Which is how do those who are frontline workers interacting with human populations in making, these kinds of consequential societal decisions, how do they go about doing that? How do they use their judgment to make these decisions? And over here, what we're going to do is, instead of examining how AI impacts people, we're going to use AI as a tool to understand how people make decisions. So what we do in this case is we actually look at this exact sort of allocation system that I already told you about. And we're trying to figure out, can we recover some rules that tell us who gets assigned to emergency shelter and who gets assigned to transitional housing? Okay, so this is sort of related to a number of different literatures actually. So I talked about street level bureaucracy. It's also related to the work of Neil on clinical versus actuarial decision making. Like what do clinical decisions look like in these kind of situations? So the first question is, can we learn rules using a simple model? And so what we try to do is we try to learn what we call a short decision tree. That is something of which you can read off sort of rules that are pretty easy to look at and see. So for example, if you read down this, you can see, okay, if this ratio of number of calls to wait time is higher than 0.01 and the gender is female and the monthly amount earned is less than or equal to $1,800 a month, then this household should go to emergency shelter. Right? Those are the kind of rules we're talking about here. And the reason why we're doing short trees is we can imagine people using heuristics like this in order to make these decisions. Okay? So we find that if we constrain ourselves to these short trees, we can achieve AUCs, which is one of the traditional measures of machine learning systems. Basically, how good are you at discriminating between a positive example and a negative example, of about 0.76 to 0.87 in this task of deciding whether somebody should go to emergency shelter or whether somebody should go to transitional housing. More complex models, in this particular case gradient boosted trees, can actually achieve much higher AUCs, which show that these frontline workers are consistent in their decision making, even beyond what can be captured through simple sets of rules. But the thing that we're really interested in is trying to understand the impact of what we call discretionary decisions, those that are not well explained by simple rules, right? What are caseworkers doing in that case? And so in order to examine this, what we do is we look at misclassifications, right? Things where the simple tree would say this household should go to one of the interventions, but it actually goes to the other one. So we're going to look at these two cases, predict to go to emergency shelter and go to transitional housing, which means that they got more intensive intervention than predicted, and vice versa. And so the questions we ask is, who are caseworkers applying their discretionary judgment on, and do these folks benefit or not? And we're going to measure benefit the same way we have been, which is the probability of re-entry to the estimate. And I'm just going to show you two results to close, and then finish up with that. So first of all, these are non-parametric statistical tests. I won't get into the details of how to talk about it later if you want. But the first result over here is showing that in both of these cases, regardless of whether when you're making a discretionary decision to either move someone to a more intensive intervention or to a less intensive one, in both of these cases, these discretionary judgments are being made on less vulnerable households. That is, ones that don't have some of these markers of vulnerability, which presumably would open up these decisions to more scrutiny in those cases. So that's kind of like logical to think about, okay, the people you're willing to sort of, use your judgment on are the ones where you don't have too many of these markers that would like really call them and into question in these cases. That's point number one. The second one, though, which I think is really interesting, is this. Suppose we actually look at the expected change in the probability of re-entry. What this graph, what this test shows is the following: that for those who get moved from emergency shelter, which is what we would have predicted, to transitional housing, that is the more intensive one, their expected gain is higher, substantially higher than you would expect from a sample of the same size taken from that population. So everybody would benefit positively if you look over here, right? The expectation is that, by moving a random family to transitional housing instead of emergency shelter, they would gain by about 0.03 percentage points. But for the ones who are actually being moved, it's more like 0.035. Right, so that's actually a meaningful kind of difference over here, and it's way out of the zone of statistical significance. But at the same time, for those who are being moved to the less intensive intervention, you don't see a similar sort of unexpected drop. You do see a drop just because it's a less intensive intervention, but clearly what this means is the human caseworkers are able to pick up on something. And obviously, they don't have access to any of this sort of sophisticated prediction information. They're able to pick up on something that's allowing them to make valuable decisions, moving people to interventions where they're expected to do better, even without sort of, necessarily being able to sort of capture that in the model. So there's something really interesting going on in the kinds of decision making that they're doing. And this sort of goes to support that there is some value. Maybe they're picking up context that we can't tell from the data, from, who's coming to the interview when the intake is happening, what else can we tell about them, and so on. So anyhow, just in conclusion, right, I've tried to give you some examples of the kind of things that we're talking about, but in like many of these high-stakes social judgment decisions, we're using machine learning all the time. We're using AI in many, many different ways, and it's usually being used for measurement of one kind or the other. So thinking about what we're measuring and why we want to measure it is actually, I would say, like, if we can solve that problem, we will solve 50% of the alignment issues of AI in these kinds of social service settings. However, allocation is intrinsically a social and political question, right? We're not necessarily optimizing for some kind of societal loss function that we know. We're instead optimizing for a very complex set of criteria that has led us to these different prioritization schemes. Therefore, when we throw an optimization term in there and just be like, okay, let's differentiate over this and try to figure out the maximum or the minimum, we're often sort of going in the wrong direction over there. We need to think about what do we as a society actually want to prioritize in these situations. I think that the key questions for the use of AI in these domains is as we get better at this prediction problem, how can that help us in achieving our socially and politically informed goals? And secondly, I think this is really sort of, a call to arms for people to really think about how does the use of AI or machine learning interact with the work of street-level bureaucrats. And street-level bureaucrats is a very broad term, right? It includes caseworkers, but it also includes those who are teaching in our elementary schools. It includes frontline police officers. It includes everybody whose job is in some way a public-facing interaction, who's operating on behalf of the state in some form, whether that's local government, federal government, anything else on those lines. So thank you again for your time. I should point out, pretty much all of this work is done by a slew of just fantastic students that I've had over the years, in particular Laura Bocarel, Amanda Kubi, Tasmin Mashiach, and Sanmay were involved in the work that I presented over here. All of this is done in very close collaboration with Patrick Fowler, as I mentioned earlier, who's my partner in crime on most of this stuff. Also, some of this was joined with Zuzana Rambala and Evgeny Borovichin. And thanks a lot over the years for support from the U.S. National Science Foundation and various other funding agencies. So thank you very much.